We've already talked about the fact that the gradient on a curve changes depending where you are on that curve. So it's not like a straight line where it is a constant value, either negative or positive. With a curve, it can change between negative, positive, and zero. So looking at this example here, what I'm going to do is indicate to you where the gradient is negative to start off with. So anywhere that the gradient is going down, so here and here, they are negative gradients. So they're all negative when it's going down. The gradient is 0 at the turning points. So where it turns from negative into positive, it is 0. So only at that point is it 0. And then going up, we have a positive gradient all the way up to that turning point. So this question is asking us to find where f dash of x is greater than 0. So if we interpret that as asking us for when is the gradient bigger than 0 or when is the gradient positive. And you can see from our graph where the gradient is positive, it goes from this x value right through to this x value. So what values are they? We're going from -1 up to 5. Now, are we including those values? No, we're not, because they're the points at the turning point, and at the turning point we know that it is 0. So we are going from -1, but if we use interval notation, it would be -1 up to 5, and again we have round brackets. If you were going to use set notation there, it would be x is greater than -1 but less than 5. Okay, that's for when the gradient is positive. What about the next one? What is that asking us? That's wanting f dash of x. Again, f dash of x means gradient, and it's looking for when the gradient is negative. So where is our gradient negative? You can see it is the purple part there. So it's in 2 bits though, isn't it? So it's going from negative infinity, remember always a round bracket with negative infinity, up to -1. That's the first time that it's negative. Again, we're not including that -1 in union, so and where is it negative again? It's negative from 5. Notice we're only looking at the x values because it wants the x values, x such that. And we're going up to positive infinity. Again, round bracket. How is that written in set notation? Well, again, we should probably do it like this, x such that, and we'll come back and fix the other one up in a minute. X is less than -1 in union with x such that x is greater than 5. And if I go back up and finish that other one in set notation there, that would also be x such that. Okay, and realistically, because our question is asked using set notation, we should probably use set notation to answer the question there. What about the last one here? It's asking me find the values of x when the gradient is equal to 0. And when is the gradient equal to 0? At this point and this point, so at the stationary points. So my x values, x is equal to -1 and x is equal to 5. So at those two x values, my gradient is 0. So let's interpret the mathematics into English first so that we know what we're doing, and then we can answer the question. With these questions, what we're wanting to do is draw the graph of the derivative function. And so we are going from the original function with f of x to f dash of x. So if you like, if we go across here, we're looking at dy dx on this axis and x. Now, certain things that you should know. First of all, the derivative function is always a degree. The x value is always one less than the original. So if you had a quadratic to start with, then your derivative function should be a straight line. If your original function was a cubic, then your derivative function would be a quadratic. So x cubed goes to x squared, and we'll talk about the straight line in a minute. So a is a quadratic here, and so we know that this is going to turn into a straight line. We need to pick out certain bits. So we're going to look at where our gradient would be 0, and that's always at the turning point. That's when x is equal to 3. So if this is 1, 2, 3, at x equal to 3, my line will cross because I know that dy dx is going to be equal to 0. Now, what happens either side of that point? Well, you can see here positive gradient and negative gradient coming from this way. So anything below the x-axis will be a negative gradient. Anything above the x-axis, because dy dx is positive on this side and negative on this side, so therefore we know that our straight line is going to go like this. So it has to be on this side of 3, it has to be negative, like it is over here, and on this side of 3, it has to be positive. So remember, positive above the x-axis, negative below the x-axis. On the x-axis is when your gradient is equal to 0. All right, let's do a few more. We do need to be careful with straight lines, but we are still pretty much doing the same thing. So here we're going across to the derivative function. Again, this is dy, dx and x. Now, what do we know about this straight line? Okay, there are no turning points, there's no places where the gradient is 0, but we do know that you've got this coordinate here, which is when x is 0, y is 1, and you have this coordinate here, when x is minus 1, y is 0. So we can actually find the gradient of that straight line. M is equal to y2 minus y1, so 1 minus 0 over 0 minus minus 1, so 0 plus 1, and of course the gradient is a positive 1. Now we could have just done that with rise over run. But it means that m is equal to 1, or if you like, dy dx, the gradient is equal to 1, a positive 1. So our line, dy dx is, if I have a scale there, all right, that's 1. So all I need to do now is draw a straight line through where x is equal to 1. And that is my derivative function for that graph. So a straight line will become a straight line, but it will become a horizontal straight line going through your dy dx axis at the gradient value. All right, one more. Here we've got a cubic. So straight away we know that our derivative function has to be a quadratic. So dy, dx and x. And again, let's pick out the bits that we know straight away. At x equal to negative 1.5, my gradient is 0. And at x equal to 1, my gradient is also 0. So 1.5 is here. So my gradient is 0 at 1.5. If that's 1 and that's 2. Negatives. And that's positive 1, positive 2, and again here is my other place where my gradient is 0. Now let's check out the gradient around those 2 points. So when we are looking at less than negative 1.5, we have a positive gradient. Between negative 1.5 and 1, we have a negative gradient. Remember, I'm only looking at the x values here. And between 1 and infinity, okay, so going off in this direction, again, we have a positive gradient. So we know that our graph has to be a quadratic, and we know that between our two x values here, between negative 1.5 and 1, that we have to be below the x-axis. It's not going to be a straight line, obviously. This is where my quadratic is going to dip. It has to be underneath. Now, I don't know how far it goes down. I haven't got enough information to draw that. All right, I also now know that anything bigger than 1 is above the x-axis because it's a positive gradient, so it goes up like that. And I also know that on the other side of 1.5, that it goes up as well. So that is the point 1, 0, and negative 1.5 and 0. And that's all the information that I can get from that graph. With the next example, we have to recall a few facts that we do know about gradients. So let's have a look at what's required here. Find the coordinates of the points on the curve with the equation y equals x squared minus 7x plus 8, at which A makes an angle of 45 degrees with the positive direction of the x-axis. You might recall to find the gradient that m is equal to tan theta, where theta is the angle with the positive direction of the x-axis. So here we know that m is equal to tan of 45 degrees. So let's have a look. We're going to do part A first. Find the coordinates of the point of the curve with the equation that at which the line makes an angle with the positive direction of the x-axis. So if m is equal to tan of 45 degrees there, so m is also therefore equal to 1, because tan of 45 degrees is 1. Now, here, dy dx is equal to 2x minus 7, because that is the gradient of that curve. Now, where the tangent touches the curve, if you think about a curve, okay, the tangent touches the curve at a point, and at the point where the tangent touches the curve, the gradients are equal. So if the gradient of the curve is m1 and the gradient of the tangent's m1 is equal to m2. So here we've got the gradient of the tangent, it is 1, and the gradient of the curve is 2x minus 7. So therefore we can say, and if you want to call them m1 and m2, they're equal to each other. So 2x minus 7 is equal to 1. That's where the tangent touches the curve. 2x is equal to 8, so x is equal to 4. And so therefore, all right, we've got one of the coordinates already. How do we get the other? Well, we substitute it back into the original equation. So the original equation was y equal to x squared minus 7x plus 8. And we know x is 4, so y is equal to 4 squared minus 7 times 4 plus 8. 16, take away 28, plus 8 would give you negative 4. And so therefore the point at which our tangent touches the curve is when x is 4, y is negative 4. Okay, in part B, we're told that the tangent is parallel to the line y equals minus 2x plus 6. Now, if we think about that on a diagram, here's our curve, and minus 2x plus 6, so it'd be a negative gradient. So the tangent would obviously be going in the negative direction because our line y minus 2x is parallel to that tangent. So that's the tangent there. And that's the line y equals minus 2x plus 6. And what do we know about parallel lines? We know that they have the same gradient. So that must mean that our tangent has a gradient. M of the tangent must have the same gradient as that line, which would be -2. We know that our gradient of our curve was 2x minus 7. Okay, so the gradients are equal to each other where they touch the tangent touches the curve, and so therefore we've got 2x minus 7 is equal to minus 2. 2x is equal to minus 2 plus 7, which is 5. So x is equal to 5 on 2. So we are letting the two gradients, the gradient of the curve equal to the gradient of the tangent. All right, that's how we get that equation. And so x is equal to 5 on 2, and so substitute x equal to 5 on 2 into the original equation, which was x squared minus 7x plus 8, and so you get y equal to 5 on 2 squared minus 7 times 5 on 2 plus 8. And let's simplify that. So just getting everything on a common denominator there and tidying it up, you get -13 on 4. And our final answer there, remember we wanted the coordinate where the tangent touches the curve. So that point where the tangent touches the curve is when x is 5 on 2 and y is minus 13 on 4.